All right, so today is our last lecture on entropy. So we went over at the beginning, right? We started talking about the second law of thermodynamics, which is like super long. Remember, we say like the second law of thermodynamics is like any heat engine cannot transfer 100% of your random molecular energy, which is heat, into ordered mechanical energy like work. But we don't know what exactly does that mean. But along the way, we defined our what is a heat engine, what is a reversible heat engine. We proved the Carnot principle, which is saying the reversible cycle or reversible engine is the most efficient engine. And then from the Carnot principle, we went over our Carnot cycle, which contains 2 reversible isothermal steps and 2 reversible adiabatic steps. From the Carnot cycle, we find out that there exists some kind of state function, which is the heat reversible over temperature, right? We define our entropy as an extensive state function. So our S is an extensive state function. So today we'll take one step further, trying to explain what exactly is entropy. So far we went over how to define entropy, how to calculate the change of entropy between your state 1 to state 2. And in this lecture, we'll first go over a discussion to relate entropy with equilibrium, or talking about what is the change of entropy for reversible and irreversible processes and link it to the overall change of entropy for the entire universe. That's our first step. Or the other way to put it is we want to use entropy and now give the second law of thermodynamics, or use the second law of thermodynamics to give a more easy to remember version of the second law of thermodynamics. And then in our second part, we'll try to build a link between entropy and some other property that's more intuitive to give entropy an actual physical meaning. All right, so that's our 2 overarching goal of today's lecture. So let's get started with our first one, which is talking about entropy, reversibility, and irreversibility. So before we get started, again, so far remember we calculated delta S for the system. So if we now move our eye into the entire universe, what do we know about the universe? Remember, we talk about the universe contains your system and the surrounding, right? The system is a part of the universe we care about. The surrounding is the rest of the universe that interacts with the system. Or the other way to put it is we have universe contains a system and a surrounding. Or because entropy is an extensive function, right? So an extensive function means it equals to the sum of each of its parts. So if we're looking at the delta S of the entire universe, we can say that equals to the delta S of the system plus the delta S of the surrounding. This equation is true because S is an extensive function. All right, so the first part, talking about a fully reversible system, we're just using, but before talking about fully reversible system, we're just using the extensive nature of entropy to write delta S universe equals to delta S system plus delta S surrounding. And then we'll look at reversible processes and irreversible processes to get an idea about what does delta S of universe look like. So we start from the fully reversible processes. So what does a reversible process mean? So in this class, one of the area we should focus on is what exactly is the definition behind each of the terms we're using. So for example, when we say a reversible process, let's imagine a specific scenario like heat transfer. So when we have reversible heat transfer, what that means is all heat flow are reversible. Or what does reversible mean in this case when we say heat flow is reversible? We're saying the heat flow from and to the system have same magnitude. This is also quite intuitive to understand. When we say reversible process, we're saying, hey, the heat into the system always equals to the heat out to the system, and it's a very infinitesimally small number. Or if we translate this into equation that we know, like when we say Q system, we are talking about the heat flow into the system. And at the same time, in my isolated system, the system is only interacting with the surrounding, right? So because they have the same magnitude, my Q surrounding well equals to negative of Q system for reversible processes only. So my Q surrounding equals to negative of Q system only for reversible processes. And then we're ready to use our definition of entropy to solve for the total delta S of the universe. And obviously, we have ds universe equals to ds system plus ds surrounding. Now, using the definition that ds equals to dq reversible over temperature. Now, in this case, on the left-hand side, my dq reversible will always cancel out with the right-hand side, because this part is my ds surrounding. Or the take-home message we're trying to say here is for a system, or for an isolated system, or our universe, right? For my entire universe, my delta S always equals to 0 if only reversible processes are taking place. All right, so this part should be quite intuitive. Just say the overall change of entropy is 0 if only reversible processes are considered. All right, so that's our first part, reversible processes. Next, we will move into irreversible processes. And in this case, we'll focus on some kind of adiabatic irreversible processes just to make our life easier. So remember, we have seen this kind of PV diagram. Each dot here represents a specific thermodynamic state. I copy-pasted from our Carnot cycle. It doesn't need to look like this, just random points on the PV diagram. Now imagine the way we built this system is we want to have the delta S between my point 1 to point 2. All right, so what we want is the delta S of 1 to 2, which is irreversible adiabatic process, and that equals to S2 minus S1. So how exactly are we going to calculate or have an expression for the S2 minus S1? So in previous examples, you can do it by building like irreversible paths between 1, 4, 4, 3, 3, 2. Or in this case, we can do it by creating a cyclic process. So in this case, what we're trying to do here is finding the delta S of this irreversible adiabatic process between 1 to 2. So this dashed line represents it's irreversible. And we're talking about delta S 1 to 2 or S2 minus S1. So a little bit different from what we did before. This time, we're trying to build a cyclic process containing this irreversible step. So we're building an irreversible cyclic process. Now, this irreversible cyclic process obviously contains a process between 1 to 2, and then 2 to 3, 3 to 4, and then 4 to 1, back into the entire cycle. Or we can write my overall S, well, equal to the delta S between 1 to 2 plus delta S of 2 to 3, delta S of 3 to 4, and delta S 4 to 1. And in this process, if you write it out, we can see why it cancels out to be 0. So at delta S1 to 2 as S2 minus S1, and this is S3 minus S2, S4 minus S3 plus S1 minus S4. So we can see every term will cancel out, like what we expect. It's a cyclic process, or my entropy is a state function, so the integral must vanish to be 0. All right. Now in here, remember we take this from the Carnot cycle, so we can set these pathways. So for example, in the 2 to 3 part, this is my adiabatic reversible process. The linking the 4 to 1, that's also my adiabatic reversible. And then linking 3 to 4, that's my isothermal reversible. So in this cycle, we're trying to reproduce a Carnot cycle, but instead of having a Carnot cycle, which is all reversible, 2 isothermal, 2 adiabatic, now we have a hypothetical cycle that contains, similarly, 2 reversible adiabatic process, 1 isothermal reversible process, and 1 irreversible adiabatic process. Now we have a way to have an expression of the delta S of this irreversible cycle, right? We went over that together. So let's do this. Now this delta S 1 to 2 is the delta S we want for my irreversible adiabatic process. My delta S 2 to 3 is reversible adiabatic, so this term goes to 0. My 4 to 1 is also reversible adiabatic. This term goes to 0. Then what we have? We have a reversible isothermal process between my steps 3 to 4. So in this case, remember my ds equals to dq REB, or in this case 3 to 4, over T. Now since it's isothermal, it's constant temperature, we can write my delta S 3 to 4 equals to Q 3 to 4 over temperature. With me so far? So what do we have? Now we have this term, which is the delta S 1 to 2. That's the term we want. Plus this term, the delta S 3 to 4, which equals to Q 3 to 4 over T. And these two terms add up to be 0. All right, or the other way to put it is we have this delta S 1 to 2 equals to negative of Q 3 to 4 over temperature. So what's the use of it, right? So remember what we're trying to say is we're trying to decide whether this is a positive, negative, or 0. Right, like what you see in our midterm exam, sometimes we don't necessarily need to have a numeric answer. Knowing whether a property is positive or negative or zero is good enough for our understanding. Now in here, in order to get an idea about whether this delta S112 is positive or negative, well, my temperature is always a positive. So the key comes to whether or not my Q3 to 4 is a positive or negative number. So how do we do that? For that, we need to use our laws of thermodynamics, right? So that's the weapon we have. We have our two laws of thermodynamics. Let's use our first law first. Using our first law of thermodynamics, we have delta U equals to Q plus W. Or the other way to put it is we can write du equals to dq plus dw. So thinking about the integration over my entire cycle, we have the cyclic integral of my du equals to the cyclic integral of my dq plus the cyclic integral of my dw. Right, so on the left-hand side, my cyclic integral of the entire cycle of my internal energy is 0, positive or negative? 0, right? So this one is 0. What about my dq? We're talking about the overall heat transfer of my entire cycle, reversible or not, we don't care. Now in here, this is adiabatic, this is adiabatic, this is also adiabatic, although it's irreversible. So my overall heat transfer of my cycle equals to Q3 to 4. And this just tells me that's the work. That's the total work, whether it's done on the system or output by the system. So using our first law of thermodynamics on this hypothetical cycle, we get an expression that the work equals to negative of Q3 to 4. So that's how we use our first law of thermodynamics. And then thinking about what exactly does this work equals to negative Q3 to 4 tell us? So then we're using our second law of thermodynamics again, right? So this is where I want to pause of like emphasizing the importance of linking a actual scenario to equation and equation back to an actual scenario. Now in this case, what we want to know whether or not my Q3 to 4 or my heat is a positive or a negative number, or what's the sign. So thinking about it, let's assume this number is positive. Then because of our first law of thermodynamics, then my total work must be negative. So what does this sentence tell us? A heat transfer being positive, meaning my cycle here, my system is absorbing heat from the surrounding. All right, so this cycle here is absorbing heat from the surrounding. And the work, or the total work output, means this cycle is doing work on the surrounding. So here is why this cycle will violate the second law of thermodynamics if my Q3 to 4 is a positive number. Remember, in the second law of thermodynamics, we say like a cycle sole effect cannot be transferring the random molecular energy, like heat, into ordered mechanical energy, like work. But if my Q3 to 4 is positive, then my work must be negative. So my cycle's sole purpose is transferring heat into work. And that is violating my second law of thermodynamics. Yes. Any questions before we move on? What do you mean by their magnitudes are not equal?
You say like sole effect can't be just like Q into like work, right?
Right.
So what if like, well, I guess this would be like.
So in here, the reason we derive their magnitude are equal is using our first law of thermodynamics that energy must be conserved. since we have 3 adiabatic processes, the total heat input must equal to the negative of the work output. Or the other way to put it is by using our first law and second law of thermodynamics, we have demonstrated that this cannot be true, right? Or the other way to put it is our Q 3 to 4 must be negative. And obviously, going back to our original question, remember we're trying to derive what is the delta S for this irreversible process between my step 1 to step 2. So that irreversible delta S 1 to 2 must be positive for this specific irreversible adiabatic process. And again, we have delta S 1 to 2 equal to negative Q 3 to 4 over T. Or the other way to put it is if we're looking at a system, a closed system that undergoes irreversible adiabatic process within the system, we have the delta S of this system larger than 0 for irreversible adiabatic process, assuming this is a closed system. And taking this one step further to move it from a random adiabatic process in a closed system, what exactly is an isolated system? Now, if we think about the definition of an isolated system doesn't transfer heat with the surrounding, so it's adiabatic. It doesn't transfer matter with the surrounding, so it's closed, right? So an isolated system is by definition closed and adiabatic. Or we can simplify this criteria here to say the delta S of an isolated system is always larger than 0 for irreversible processes. Okay, so that's the system within that isolated system. And taking this one step further of thinking my entire universe is a big isolated system containing system and surrounding. So what we have as the end of this part of the derivation is my delta S of the entire universe is always larger than 0 for irreversible processes, or my delta S system plus my delta S surrounding will always be larger than 0 for irreversible processes. All right. So this part is a little bit abstract, but effectively what we're doing is not doing any real calculation, but just trying to derive using our first law and second law of thermodynamics, what are these terms? Are they 0? Are they positive? Are they negative in a hypothetical cycle? And then we're ready to rephrase our second law of thermodynamics in some way it's easy to remember. So going back to our second law of thermodynamics again, what we're saying is that there exists this state function, entropy. Now, the total change of entropy of the entire universe is always greater or equal to 0. It equals to 0 for all reversible processes. It's greater than 0 for irreversible processes. And then we have definition of the state function entropy equals to dq reversible over T. So I will have ds equals to dq reversible over T. All right, so in this first part, we spent some time talking about a hypothetical irreversible adiabatic process. We created a cyclic process containing this irreversible adiabatic step. Right, so this entire cycle is irreversible. But the total delta S still equals to 0 because it's a cyclic process. And then from this cycle, we derive that delta S 1 to 2 for that irreversible adiabatic process equals to the negative of Q3 to 4 over T. Then we use our first and second law of thermodynamics to derive that Q3 to 4 must be a negative number, and hence the delta S for this irreversible adiabatic process in a closed system must be greater than 0. And then we took some logic step ahead to say, hey, this is generally true for the entire universe if we consider the entire universe as an isolated system. All right. And now we have our second law of thermodynamics, right? We know that delta S is 0 for reversible process and delta S is larger than 0 for irreversible process. Let's connect it to something like we are more familiar with as chemists, which is equilibrium. So what exactly is the relationship between entropy and equilibrium? So this is a common misunderstanding. I want to go very slow here and try to rationalize it. The thermodynamic equilibrium in an isolated system is reached when the system's entropy is maximized. All right, so the entropy S is maximized when we reach equilibrium. How do we rationalize it? Imagine we have a plot on the y-axis, that's entropy. On the x-axis, that's time. That's how long we take to reach equilibrium. Now, this cross here means we have reached equilibrium. Now, prior to reaching equilibrium, my processes are irreversible. We're moving towards equilibrium. So we have irreversible processes prior to equilibrium. Or for irreversible processes, we have our ds larger than 0. Once we reached equilibrium, we know that ds equals to 0 at equilibrium. Because at equilibrium, we only have reversible processes taking place. And that's where ds equals to 0. And that's the maximum point for our entropy curve. All right, so the common misunderstanding here, just read this sentence again. So thermodynamic equilibrium in an isolated system is reached when the system's entropy is maximized. Now we're ready to try to rationalize what is the physical meaning of entropy. Now we know that based on our understanding on reversibility and irreversibility, we recognize that entropy is maximized at equilibrium. We can ask ourselves another question. What else is maximized at equilibrium? So I'm going to jump one slide. These are just review. But let's just jump to here, talking about the physical nature of entropy. What else is maximized at equilibrium? Now, instead of thinking about any equilibrium, let's just fix our mind to think about our mixing of inert perfect gases. At constant P and P. So that's the example we did in our last Wednesday's lecture. Remember, mixing of two ideal gases is an irreversible process, right? So what exactly is happening? Knowing like these criteria, we know that perfect gas molecules do not interact with each other. We know that the motions of my gas molecules are completely random. And then thinking about why mixing of my ideal gases is irreversible. So, or the other way to put it is what is maximized at equilibrium. So I did a little simulation here. I'll post my code. I write a little Python code to do the simulation. Remember, we have initially, let's imagine we have two different types of ideal gas molecules, red and blue. In the initial state, we put all the red one on the left, we put all the blue one, well, all the blue on the left, all the red one on the right, whatsoever, on each side. 500 dots. And then I ask my script to give each dot a random velocity and random direction, and ask it to start moving. Right? For every step, my dot will move in a random direction at a random velocity. After 150 step, so I'm simulating my number of particles, number of red on the left, number of blue on the right, so that's what each curve means. We're simulating that against simulation time, or like steps. What we find out is give my system enough time, my number will eventually drop to about 250 on each side. We see small fluctuation, and that's because I only have 500 dots. Imagine you have one more of gas molecules on the left, one more of gas molecules on the right. So that fluctuation will be much smaller when we have more and more number of molecules to consider. I can't run one more of simulation there, but 500 gives you a good way to think about, right, eventually our system will stabilize around my equilibrium. All right, so at my equilibrium, what we have is this equilibrium thermodynamic state of an isolated system is the most probable state. All right, so if we ask the simulation to take like infinite amount of time, ask it to run for whatever time we like, eventually the most likely we will end up into some kind of final state like that. All right, so this is just a quick demonstration in what exactly is maximized at equilibrium, right? We used our laws of thermodynamics to derive that entropy is maximized, and using our intuition and little simulation to demonstrate that probability of that thermodynamic state is maximized. And now let's do the derivation together to see how exactly my entropy is linked to probability. But before we do that, let's see if we have any questions on this part. Nope? Okay. Now let's do our derivation. Remember, in our previous case, we did this calculation of mixing of my ideal gases into calculate delta S of the mixing of the ideal gas. I'm just going to put that delta S on the board, and we'll later on come back to it. So in our previous derivation, we find out that delta S of mixing of two different gas molecules, say A and B, we have that equals to N, well, this time we had D and E, so let's write ND times R ln mole fraction of molecule B minus NE R ln times mole fraction of my molecule E. So that's our calculation from the laws of thermodynamics. And now let's do the derivation with probability and see how do we get the same answer. Now in here, first of all, what is the function of entropy as a function of probability? So the way to think about it is, let's just assume we have a entropy as a random function of probability. So this P here is probability in our writing. Like, I do not specify what it is, we just say S equals to some function of probability, right? Because the whole point we're making here is we demonstrate that both probability and entropy are maximized at equilibrium. So they must be linked somehow, but we don't know what exactly is that link. So now we're trying to find out what is this function here. So considering our system, remember we're talking about mixing of two ideal gas in separated chamber. So we can think about our total entropy, or S of the entire system 1 plus 2 equals to S1 plus S2. So again, this part is only using the extensive nature of entropy. All right, so the entire S of my 1 and 2 equals to S1 plus S2. That's the extensive nature. We draw the partition in the middle, assuming. Or, since we say entropy is a function of probability, we can write it as some kind of function of probability of 1 plus 2 happening together equals to f of P1 plus g of P2. So this h, f, and g, just random function. They're the same type of function. We don't know what exactly they are. All right, so this is just using the extensive nature of entropy and then write this random function into our extensive nature of entropy. Now, what is the probability of 1 and 2 happening at the same time? Now, in probability theory, when we say the probability that two independent events both happen is the product of the probability of each event. Like you toss two coins, like 1 time, 2 time, these are independent from each other. The probability you get 2 heads is, well, 1/2 times 1/2. Or the other way to put it is we have the probability of 1 plus 2, so event 1 and event 2 happening at the same time equals to P1 times P2. With me so far? And what exactly do we have now? So taking these two relationships together, that is using entropy's nature as an extensive function and probability theory, we end up getting, say, some random function of P1, P2. So that's saying, that's using this relationship here, equals to the same kind of function of P1 plus that same kind of function of P2. All right. I don't have the proof for you, but you have to trust me. The only solution to this equation is a logarithm function. So for example, if you have ln x, y, that equals to ln x plus ln y, right? So a logarithm function is the only solution for this setup. Or the other way to put it is we have entropy as a function of some constant times ln of the probability plus a. And a and k are constant here. We'll come back and say what exactly are a and k in this example. All right. Now we have an expression of entropy. Going back to our original setup, remember we're trying to solve the question in what is the entropy of mixing of my ideal gases? Now, how do we do that? Instead of using the laws of thermodynamics, let's solve this problem using probability. Now, what we want to have the probability of my second event happening, or this situation. We also want my probability of this situation. Now this P2 is quite straightforward. This one is already at equilibrium, or when we dealing with an equilibrium state, we say the probability of that equilibrium state happening is only infinitesimally smaller than 1. Or we can say P2 is almost equal to 1. All right. But considering this intermediate state, so remember this is the state when we first remove that partition. How do we calculate the probability of this specific situation? Now thinking about what are the things in here. If I call my atom D as my blue dot. So the probability that all blue dots in left half is, well, 1/2, right? So for each blue dot on the left, assuming we partition it evenly, so each blue dot will have 1/2 of the probability to stay where they are on the left half. But we have, in this case, say, number of molecules. So the number of D will be product together. All right, so the probability of all my molecule D on the left-hand side is 1/2 to the power of ND, where ND is a number of molecule D. With me so far? Likewise, if we call these E, assuming we partition it evenly, the probability of all the E in the right half will be 1/2 to the power of number of molecule E. And this 1/2 is only true when we partition it evenly. Right, you can have 1/3 and 2/3, or like 1%, 99%, just making your life very hard. But now let's just keep to 1/2 for now. So what is our P in this case? Our overall P equals to the product of the two events happening. So that's the 1/2 to the power of ND. That's all my molecule D on the left-hand side. And 1/2 times number of my molecule E. All right. And let's make our life easier by assuming my ND equals to NE. We can further simplify this P1 to be 1/2 to ND. And in here as well, we can also simplify it. We'll do it later. And since P2 is 1, we have an expression for our delta S using our probability definition. And that is my delta S is S2 minus S1, that equals to K ln P2 over P1. And again, P here is probability. Don't misunderstand it. Now we know that P2 equals to 1, P1 equals to 1/2 to the power of 2 ND. We can write this out as 2 NDK ln 2. All right. So that's our expression coming from our probability theory. Now we are ready to answer the question, what is our K here? And to answer that question, we want to continue doing our derivation using our original approach. That's now we know that my number of mole of D equals to number of mole of E. My chi D thus equals to my chi E equals to 1/2. So these are only true when we tell you that's the case. And then we can simplify our delta S mix equals to, well, 2 times ND R ln 2. So this is 1/2 and becomes 2, and the negative becomes positive, and we add them together to have the 2 NDR. All right. So what do we have? Now we have two expressions of my delta S mix. This comes from my thermodynamic calculation, building the reversible path and solve it using our definition of entropy, or solve it using our probability term that equals to 2 number of mole of molecule D times K times ln 2. Or the other way to put it is we can end up having my K equals to R divided by the Avogadro number. So that's R is our gas constant. And NA is my Avogadro number. And K equals to 1.38 times 10 to the negative 23 joule per Kelvin. And this is our Boltzmann constant. And that's one of our universal constants. Remember, we have well, I guess I shouldn't say remember. So in the SI unit system, we have 7 universal constants. And the Boltzmann constant is a constant related to the definition of temperature or Kelvin. And here's where we actually make the link. All right. So as a practice question, I highly recommend you go to your midterm exam. We'll hand you back the exam on Grayscope. Once you get that exam, remember in our problem 2-5, we did the calculation using this equation. Now redo that calculation using our probability theory and check your answer with the thermodynamic approach. They should give you the same answer. All right, so that's a nice example nice practice example you can do. And let's see if we have any questions. This lecture is more on the abstract end, but it's very important for you to recognize or to go beyond all the equation derivation to give entropy a physical meaning. So what is entropy? And it's a form of probability of a thermodynamic state. So if you're going to remember anything from this entire chapter, please remember entropy relates to probability. All right, see if we have any questions. I'll also post the code later on of this little simulation. So feel free to alter the number of your red and blue dot. Like for example, if you make that number very small into like 3 or 4, you'll see that fluctuation is going to be very big. So that corresponds to our random movement of the Brownian movement. So there will always be fluctuation over the equilibrium, but the more number of particles we have, the smaller that fluctuation. Or the whole point is, the more number of particles we have, the larger the entropy penalty it is to go back to its original state. Okay. We have 2 more minutes left. See if we have any questions. Yes?
Can you just show how you got from the first expression to the second?
This one?
Yeah, can you just
Oh,
show
yeah,
that
sure.
real quick? Thank
So
you.
this one, so this one, we have the number of ND, R ln 1/2 minus number of E, which equals to D, R ln 1/2. Right, so this ln 1/2 equals to 2, ND equals to D. So we have NdR ln 2 plus NdR ln 2, that equals to 2 NdR ln 2. All right?
Thank you.
Okay, if there's no more question, remember to fill out the survey. We'll have your grade out as soon as possible, hopefully later today, if not tomorrow. And that's all from today.